So first of all, look at these three alkali metals, and you can see lithium conducts electricity, sodium conducts electricity, and potassium conducts electricity. Now let's see the metallic luster. Lithium is a little harder than the others. Let me see if I can cut into it. There we go. Oh yeah, very shiny. Look how shiny it is, right? See how shiny lithium is? Okay, I'm hoping you can see that now. And then sodium, let's cut this open. Just for a moment, it's very shiny, and then you can sort of see how that fades, right, as it's reacting. The potassium, let's try to see the shiny surface on this one. This is all the potassium left after the demo, so I don't know if you can see that. Anyway, so potassium, again, it's like super squishy, almost might as well be clay, but it's a kind of clay that bursts into flames and explodes when it's in the presence of water. So I'm going to put that back under oil. I'm adding the universal indicator. Here we go. I'm going to put a squirt in there, squirt in there, squirt in there. Hopefully you can see that color. Hopefully the universal indicator, the color is very clear. So that is neutral. So now I'm going to put the lithium in. I'm going to drop them in. Watch what happens to the color, if you can see the color. And while that's going on, I'm going to get the sodium ready before we lose our lighting. So notice the change of color. The change of color is rather dramatic. Now I'm going to put in the sodium. So ready? I'm going to drop it in. Watch what happens to this shape. Boom! There goes the beaker. Very flashy, very flashy. Don't worry, I've got safety equipment. That was expected, sometimes it breaks the beaker. Here is the potassium. Again, it's less than a milliliter. Look how shiny it is. And I'm going to drop it in and run. Because it was broken into a bunch of pieces, it reacted more slowly. Because it was made up of several small pieces, it did not actually break the beaker this time. Okay, but pretty dramatic reaction for potassium nonetheless. The metallic shine for sodium. So ready? I'm going to drop it in. Watch what happens to this shape. Boom! There goes the beaker. Very flashy, very flashy. And I'm going to drop it in and run. Because it was broken into a bunch of pieces, it reacted more slowly. There's sodium, ice lighting something on fire, doesn't happen a lot. And sodium, potassium's already gone. Let's put pot. Didn't break the beaker. In the reactivity lab, we are looking for a trend in the reactivity of different metals. We're using only metals on the periodic table. We're going to try to piece together the direction of the trend. Which direction do they get more reactive? We're using hydrochloric acid. This is universal indicator in here, which is making it red. It's not food coloring. Remember, universal indicator shows when something is an acid, when you get that color. And if it stops being an acid, well, then it stops being that color. You'll wind up with something else, okay? We are going to put about 20 milliliters of HCl into each of these different beakers of different metals. And they're in various grain sizes. Most of them have some kind of powder in there mixed in with larger grains. So it's pretty fair, not exactly fair, but we can tell by the reaction rates which one of these reacts the most. So you might say whichever one of these reacts the most should be number one, but don't forget the demos, the alkali metals that we did outside, lithium, sodium, and potassium. Well, they were only fighting water. But if you remember the demos with those three beakers, well, they certainly reacted with water. None of these would actually react with water. Well, maybe one of them would, but not as dramatically as what you saw in the demos. So for the ones we saw in the demos outside are definitely number one, number two, and number three, okay? So here we have 6 more. So they're going to be starting with number 4. Whichever one of these is the most reactive indoors with hydrochloric acid, which is much stronger than water, that's what it's fighting, much stronger than water, well, that'll have to be number 4. And then the next one will be number 5, then 6, 7, and then the least reactive of all of these is going to be number 9. So the ranking, the reactivity ranking is actually the main thing we're looking for. We want to record anything we see, like a change of color, bubbles, smell, any of those things. But the main thing we're trying to figure out is putting them in order of ranking. On the first page of the lab, that's where you record information about the demos. Okay, if you didn't see the demos live, then watch the video of the demos. And you know, those are definitely going to be number 1, 2, 3. You have to figure out the order. And then the ones inside, like I said, are going to be 4 through 9. And once we know those rankings, those are the numbers that are going to go onto this little periodic table. The F block has been removed here. It's the chopped periodic table because we don't have any here from the F block. No uranium, sorry. So once you plot them on here, you can sort of see which direction the trend is. Up, down, left, right, diagonal up, diagonal down to the left, diagonal up and to the left. Whichever direction they get more reactive. That's what we're talking about when we say a trend. So you want to try to devise as much of the trend as you can. Now the trend for this is not completely obvious. So what you're going to want to look for is where the low numbers are, those are the more reactive ones, and where the high numbers are, those are the less reactive ones, and then draw an arrow pointing toward the lower numbers. That pretty much is going to give you at least part of the trend. Then we have some other things here with electron configurations. That's to practice your electron configurations. And some of these lie in the D block, and that makes it a little trickier. So just try your best with those. I want the full electron configuration starting with 1s. And A, of course, is magnesium, okay? Another thing, of course, it's fairly easy, but you've got to put the name of the metal and the symbol from the periodic table. Well, some of these are exceptions to English, so their symbol will not match their name. Just remember to get the symbol right as well as the name of the metal. And then don't forget to put some kind of notation, anything you observe. And if you're relying on the video, my assistant, my tiny assistant, will have to provide you with the smell. She'll let you know if there's a smell, but you can see if there's slow reaction or no reaction, possibly. Maybe one of these won't even react. Or, moderate reaction, bubbling, fizzing, gas coming out of it, evolving. So basically just anything you notice, change of color. Remember, this is starting out red. And then one other thing we're gonna do is we're gonna get the temperature afterwards. Well, we're gonna get the temperature. These are all the same temperature right now. I just poured these out of the same beaker. We're gonna get the temperature of those to begin with. And then after the reactions, we're gonna get the temperature of each one, and we'll be able to see if it's an endothermic or exothermic reaction. Not only that, but we can sort of use that as a comparison. So with endothermic reactions, heat is absorbed. With exothermic reactions, heat is released. Okay? So that might be another way to compare them if you can't decide. It's very important that you decide which one is more than the other to put them in order, in ranking order. So don't have a tie. Okay? If two of them are really close, maybe go by the temperature change. I don't know. Okay? So this is the Reactivity Lab, and we're about to get started. The Reactivity Lab with my beautiful assistant, Lucy, who is going to be reacting a bunch of different metals with hydrochloric acid. Each test tube has 20 milliliters. So what's the first thing, Lucy?
I'm going to take the temperature of one of these.
Okay. And we're going to assume they all came out of the same beaker recently. We're going to assume that the temperature of one is the same as the temperature of the others. So we're starting at what temperature?
It's at 24.6 degrees Celsius.
Perfect. Great. Okay. So now we know, we assume that they're all 24.6 degrees Celsius. She said it perfectly. And we're going to pour them into each of these beakers. She's going to do it pretty quickly. Not enough to spill it, but not quickly enough to splash it. But then we'll see if the reaction starts. Go ahead. First reaction. Whoa!
Oh, okay.
Well, what would you say about that?
That was very foamy, and that was a big reaction.
Yeah, it actually blasted some of the pieces out of the beaker. Okay, do you notice anything about a smell? Because students at home can't smell it.
I don't really.
Come over this way a little. Move this way. How would you describe that?
I'm not sure.
Okay, because they can't smell that.
It smells kind of like burnt.
Okay, that's fine. Now get to the next one. Maybe this time pour it just a little slower. It's okay if it foams over. Okay.
I'm gonna just turn purple-ish.
Turn purplish. Well, remember that it's already reddish because it's an acid. And then now you're pouring in, which one is this, by the way? Which one are we on?
This is iron.
So by the way, the first one was magnesium, then that was aluminum. See, is anything happening there? Okay, pour it into the iron. Okay, and we're gonna keep an eye on all of these. Okay, that one was very rapid, okay. And now we're getting to which one?
Copper.
Okay, copper, right? Let's just say each one we're pouring it into.
Okay.
Pouring it into the copper.
The next one is zinc.
The next one is zinc. So I would be careful about saying this is purple because what you're seeing is the red mixed with the cloudiness of the irons. Okay, this one is zinc.
Oh, that one got foamy.
Foamy, is it gonna go over? Is it gonna go over?
Aw.
Oh, it nearly did. Well, so that one didn't go over, but that started pretty quickly, right? So things you can say about like bubbles.
It smells like, it kind of smells like
Like what? What would you describe that as?
rotten eggs.
Okay, that's interesting. Rotten eggs. So now notice this one, it's pretty good reaction, but it didn't go over the top like the first one. So that gives us a pretty good comparison between them. Let's go back and look at how this one's doing. Is anything going on in there? This is the aluminum. Is anything going on in there?
There's a bit of bubbles at the top.
Do you see what they're doing in there?
They're growing, they're moving.
Do you smell anything coming out of this one?
Oh. I don't know how to describe that, but it's horrible.
Okay, so now this one's going really well. Okay, so now we got one more to start.
It's calcium.
Okay, let's see how this
So
calcium
horrible.
starts.
Oh. It was a bit foamy when I poured it in,
It was foamy.
and then it turned like pink.
Okay,
but
let's take a look
it's
at,
already-
wow, this one's going. So this one took a little bit to kick in.
Bleh.
Did you notice that? Took a
Yeah.
little bit to kick in, but now look at all that. And what does that smell like? Don't get too close. You sort of, what you do is you waft it towards yourself like this, if you need to. If you can't already smell it. Come over here so
I can smell it.
I want to get you in the shot. So what does it smell like?
I don't know. It's horrible.
Horrible. Okay, that's fine. Oh, look. Now what about this one?
That one is.
Which one is this? The zinc. So, well, look at that. Look at that. There we go. Well, this is going to damage some of the placards.
I think that's the most. That one's all really reactive. Now.
It's really reactive, but notice how long it took to get started, right? And then this one's really going. So it eventually did totally bubble over. Okay, maybe I can salvage this placard if I slide it back slightly. Okay. And then this one, come back over. Okay. This one's really going. So what would you say? Do you see all of them have had a reaction? Would you say that?
Yeah. Well, this one didn't have.
This one did it do anything?
I don't think so.
Okay, what about this one? Has this one done anything?
It was just moving. It looked
Look-
like it
look
got
into
a
it.
little darker.
Look into it. Do you see anything?
Bubbles.
Is that a reaction?
Yeah.
Okay, so that isn't so dramatic. Look at this. Compare that. Little, looks like little water skimmers. Compared to this, or compared to that, which went right over, or this one, or even that one. Is this one doing anything? Do you see anything?
I see bubbles on the side slightly, but no.
Bubbles. Okay, so let's keep an eye, because remember, reactions like this one, which turned out to be pretty good, took a little while. So it's a trade-off between the reaction rate, like how quickly it goes, and the extent of the reaction. So clearly some of them start really quickly, some of them take a while but then build up. This one is sort of in between. So making the decision about the ranking should be based on that. This one is still, this is the iron, still bubbling away.
So are we gonna take the temperature?
Oh yeah, get the temperatures now of each one of them. Let's start with this first one. Let's start with the first one. Temperature.
Temperature is.
Give it a little time to adjust. Oh, wow. And this is, remember, this started a while ago, right?
Mm-hmm.
But look at that temperature on there.
Is
Let's get it approximately
like 54.0.
54. And you know, that's like way over 100 degrees Fahrenheit, by the way. And Celsius temperatures don't sound as hot as they are. And that's after, it happened a while ago. Okay, let's get this next one. That was the magnesium. This one is the aluminum.
Yeah.
And give it some time to adjust. Make sure you're in the liquid,
Smelly a little bit.
but not touching the beaker.
Yeah, it's-
What is this one on?
This one is at 89.9.
89.9.
Oh, it keeps.
89 point. Okay. And you're gonna wipe it off?
Okay.
What about the iron?
Iron. It still smells horrible. Ugh. 34.1.
Okay. What about the copper?
Copper is 25.4.
Okay. What about the zinc?
Zinc. Um, 60.9 Celsius.
Okay. And what about the calcium?
Calcium is 44.4.
Did you make sure you're all the way in there? Okay. What is it again?
44.8 Celsius.
Okay. So the one thing to keep in mind is that we did not measure the temperature of this one immediately after the reaction happened. So that one had time to cool down. But the temperatures are probably fairly accurate for what occurred. And not all reactions are exothermic where temperatures go up. But usually a temperature change is a good sign of a chemical reaction. So like this one's still going. It's really going. This one's still tinkling. This one, it's kind of frothing the liquid that is left. So what I'll have to do is I'll have to neutralize the remaining acid in these. So let's take another look at the calcium one because we still have to decide here.
It's much more bubbly on the sides.
Do you know what, for these ones that haven't done too much, for the ones that really haven't done a lot, why don't we try to stir them up a little bit? Use that little stir rod and stir. Let's try this one. Let's try the calcium. Let's stir it up a little bit. Let's see. Okay.
Oh.
And then wipe off the end. Wipe off the end. Let's stir up the copper too.
Yeah, and
I don't think we need to stir this one. We can stir this one.
no, it's just moving.
Okay. And then, oh look. I see something. Do you see that?
Oh,
Do you see rising up out of here?
kind of. I see the calcium.
You don't see the gases rising up? You have to observe very
yeah,
carefully.
I see
See it? Now there's a lot coming out of this one, so you got to be careful, but there's definitely some gas rising up out of here.
I saw it.
And let's not get into whether we're actually seeing the hydrogen or the water. Oh, let's not get into that. Okay, and then what about, let's stir up the iron too. Did you wipe it off? Let's stir up the iron. Because certainly those three did the least, I think it's fair to say. Okay, now let's see. But we definitely saw some bubbling and popping in this one. And there it goes, it's still doing it. Maybe it's even doing it faster now that you stirred it. Look at this, look into, smells worse. Okay, look into there. See that little bubbling and popping? So it's bubbling, but not nearly as much as something that would generate a foam. And then we saw some gas coming out of this one, but nothing really dramatic, and it's still red. And what about this one? Did we get anything out of this? For the copper, did we get anything, Lucy?
No.
Okay, so I think it should be pretty clear based on these observations how we need to rank them. So the only reason that this one still has a little red in it, I think, is because the reaction happened so quickly that actually maybe if I plop these pieces back in. Oh yeah, oh my God. You know what, Lucy, do you know what we could do? Because I'm putting these back in. We could take a temperature one more time of this one right while it's really going.
Okay.
Because look, that's the only reason it didn't use up all the acid. Well, let it go for a second. Okay, let's get a temperature.
Okay.
Get one more temperature for the magnesium because while it's still happening. Because maybe that wasn't.
60.
Is it changing? You want to wait till.
Let's do 69.2.
69.2. Okay, that might be more accurate. Okay, so we're using up some of the acid by using up the materials that spilled over. So pretty clear about the reactivity of these. Now ranking them is a little tricky, and it doesn't have to be perfect really, but it's pretty clear which one had the least reaction, which one had the most, and then putting the other ones in order is the other trick. And also notice, the acid started out red because of the universal indicator. That means it was an acid. Which ones are still red?
This one.
This
copper.
one, copper, and
calcium is like pink.
Now it's pink.
Yeah.
So that means there's still acid in there. So it could be that we didn't put in enough calcium. It could be the reaction isn't quite done. Oh, but look, there we go. You see those bubbles? I see the popping like we saw before with the iron. The gases are making me sneeze, sorry. Okay, so now we see the popping going on there. And even more popping going on there for sure. So I think actually I would be ready to rank these. Okay, so you want to describe what you saw in the video. Make sure to write the names of the metals, the symbol, and then the ranking order. And then remember, it's the ranking order that you put in the box of the element. Let's say, if iron is here, you're going to put iron's ranking number. Let's say it's like number 5, okay? You put the 5 there. And then you can look on here and sort of see where the numbers fall, which direction the trend is. Okay, I think the reactions are winding up. This one's still going. We might get a little more video of the reactions finishing up. But I wanted to thank Lucy for remembering to take all the temperatures. Thank you. And for doing such a good job with the Reactivity Lab. Thank you, Lucy.
Bye.
Bye-bye.